focusing on dimensioning fundamentals. How to detail correctly the lengths and size and locations of particular aspects of our drawing. The focus of this text is just to basically introduce the major concepts and then to show you how to locate specific details for each individual dimensioning situation you come across. Basically, this whole chapter is full of great notes. First concept are some of the terms associated with this type of work. You have a nice little diagram up at the top of the page, and it has things like the words size and location. And those are the basic two types of dimensioning systems there are, or dimensions that we produce. For example, any part that's created may have a size and this would be a size as well associated with it. For example, you have to have sizes to create parts or cut parts out. And another example of a size, this would be a size. And then you have what we refer to as location. That's a location. That's a location. And that's a location. As well as this is location. So two types of dimensions: location and size. That's all there is. Nothing too complex about that. And that's what the book starts off in talking about. Then it breaks down into specific identifications of dimensional components. For example, the dimension line itself. What is a dimension line? Well, it turns out that there are standards associated with this whole thing. We'll actually go up a page, and it points out the American Society of Mechanical Engineers, ASME, let's see, we'll put a little notation right here. ASME Y14.5M is the standard published by the American Society of Mechanical Engineers that controls dimensioning. And standards for all drafters, and it's a text you can get for yourself in terms of basically saying, okay, do this, do this, do this, do this, do this. However, your textbook does a great job in showing the same information available. Some standards may change over time, so that's an important thing to remember. Now, in terms of terminology, we have the dimension line. The dimension line is the term that we use for a lot of things, but it really only relates to this particular item right here. See it? This is a dimension line. It is the line that is used between the leaders, the extension lines, which the extension lines, of course, are these. So terminology's point is the text or the arrows are associated with the dimension line. The line that connects to the object itself is called the extension line. Now, this little detail that you see here is a great, a great example that you should keep in your mind, because it basically gives you all the information you need in terms of sizing. For example, it says the visible gap between the extension line and the object should be 0.06, approximately. It shows you the height that the extension line should extend beyond the dimension line. It shows you the minimum spacing associated with dimensions stacked on top of each other. It even shows you how the extension line needs to pass through a portion of the center line, but not actually hit the center point of a circle. So there should be a gap there, and we'll zoom in just a little bit more to kind of detail that. There should be a gap there, there should be a gap there, there should be a gap there, and there should be these distances around. So all you have to do is pull this chapter up in your book, look at it, and say, okay, well, this is how I properly dimension an object. Here's an example of how to handle things that are bent. So you have a great little tool right here to work with. It even shows you details over on this side for dealing with notches and section views and how to dimensioning for detail drawings. So some good little tools there for you to keep in mind. If we take a look down here, we have a good example of what to do when you have repetitive features. For example, when you have 4 holes around there, or of a certain size, 2 holes anyway, you can use a number of occurrences, x, to represent multiple of, symbol, and then value. Now this doesn't mean multiply the value by this number, it means this number is repeated 2 times. Same thing down here, 0.25 diameter is repeated twice, and therefore is even thrown in a little letter to make sure you understand which one's which. And then obviously this one, since it's these are the only 2 left, have to be multiples here. I'll also show you some specifics on dimensioning for the liters, but typically the CAD program covers that. Now you see this little liter identifies the surface material, which is a nice little option instead of a note where you can just put a little dot and have that out there. Radius, 4 times the radius, means it's a radius 0.5 in 4 different locations. So repetitive features are handled very simply just by a quick modification of the dimension itself. Now we also look at dimensional notes, and figure 9.4 is it? Yeah, we go. Sorry. And it points out the dimensional notes are used with liters to describe size or form of features. It's not like a note, it's a dimensional note, which implies just basic information. For example, we see here an angular surface, a chamfer, and it just uses a liter and the notation 0.25 by 45, implying the distance is 0.25 this way and 0.25 down since it's a 45-degree angle, or 0.25 out and then 45 degrees from there. Same thing is true here. We have a dimensional note used to identify the circular holes, which can also be interpreted as a dimension itself. And then we have a note that is used for thread calls, 7/8 thread, 9 UNC, and 2A. And this is also a dimensional note, and is done very quickly and easy with most CAD packages with the liter command. So there's a lot to this dimensioning stuff that you need to be marking as we go along, and I'll point out the key figures so that you can come back to them when you run to a specific case. Now we go into sizing of different text and pieces of information for us. Let's take a look at some of that. For example, when dealing with arrowheads, it has a couple little suggestive sizes for the arrowheads themselves. Now again, this is usually taken care of by the CAD package, so it's not necessarily something that you have to worry about recreating. But the number 0.25 is listed as a typical size for text and arrowhead heights and those kind of things. Keep in mind that with most CAD packages, 0.08 or 0.09 is about as small as you can get and visibly be read. It does recommend that arrowheads be the same height as the whole numerals, usually 0.125. So there's a magic number. There's 0.125 or 1/8 is your text height and arrowhead height. There's also the concept of using dual dimensioning. And a couple of other terms to keep in mind. Fractional dimensioning shows it there. And this is just laying out how certain types of dimensioning are used. For fractional dimensioning, it's just obviously the fractional value there in the middle in place of the decimal. Typical decimal inch or metric dimensioning. Dual dimensioning, where you have both the imperial and the metric value. Or also dual dimensioning, where you actually have it in parentheses behind it. Any of these cases, just a basic format that most of the CAD packages will take care of for you, but just understanding the terms is important. For example, when we are drawing, when we have a part that may be going to a particular buyer or manufacturer, we have to keep in mind that not everyone uses the imperial system. And do that real quick. So we might have an X value in imperial and a parentheses with the metric equivalent in it. which is no big deal. The CAD package can take care of that without a bit of problem. But it's important just to realize that it's necessary often to dual dimension, just for multiple possibilities. And typically most manufacturers nowadays work in decimal inches or have completely switched to the metric system, and probably will over time. Now we have a couple concepts coming up. The dimensioning systems themselves, the difference between what we refer to as unidirectional or aligned. And let me give you a example here, what that means. Aligned dimensioning means that you align the text of the dimension with the surface or feature that you're dimensioning. For example, you'll notice that 0.25 runs this way and is parallel to the surface. However, here, this measurement, 0.387, runs this way, this object runs this way, so the dimension runs this way. Same thing is true for the overall dimension this way, 0.4. This is called aligned. It just means it's aligned or parallel with the object in question or surface in question. Unidirectional means it just has one direction no matter what. Doesn't matter which way the surface is going, it doesn't change. Typically horizontal is the only value there. And obviously the unidirectional is more clear to understand, less difficult to read, and therefore more use in practice. The aligned is very rarely used in practice nowadays. You also notice that an example of staggered, here's a good little figure of that, staggered dimensions provide a better appearance and improve clarity. So it's easy to read from one to the other and improve the quality of the manufacturer. So there's another good term to keep in mind. Okay, as stated before, we've got the whole term decimal inch dimensioning, and this is primarily the form that is used for manufacturing today, or here in America, if not metric. And that is where you have, 1.25 inches, or instead of saying 1 1/8, or 1.5 instead of 1 1/2, or 1.0625 instead of 1 1/16. This is what we like to use. This is the old style. Okay, so in decimal inch, you see that at the bottom of the page is the typical format, and there are some rules to decimal inch dimensioning, and these are important for us to pay attention to. First of all, rule number 1, omit zeros before the decimal point for values less than 1. So instead of going 0.250, you go 0.25. So you'll notice nothing's here. And you can add the 0 on if necessary. It depends on your precision levels. So it could be 0.125, it could be 0.75, doesn't matter. No 0 is put in place. That's rule number 1. Common decimal fraction equivalents, blah, 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 may be shown as 2 place decimals unless they're used to designate real or whole size and numeric thickness. So it's just saying you can go with, instead of 0.750, you can go with 0.75 when dealing with common values, like 0.5 is a common value, 0.75 is a common value, 0.25 is a common value. You can omit the zeros in those cases. You can use common fractions when denoting common sizes for materials, threads, and other features produced by tools that are designated by common fractions. Which means if I whip out a wrench, it's going to be a 3/8 inch, a wrench, excuse me. It's going to be a 3/8 hex wrench. So instead of writing out 0.375, I write out 3/8. Quarter is a quarter or fractional. These are all things that are used with reference to tools. For example, a 1/4 inch drill bit, a 3/8 wrench, a standard 3/4 inch tapping. So it's important to realize that sometimes we use fractions, but typically it involves a certain type of tool. Okay? And also, decimal points must be definite, uniform, and large enough to be visible on reduced size drawings. The decimal point should be in a line with the bottom edge of the numerals and letters which relates to. That's no big deal because of the fact that the command system does it, the CAD system does it for you. So you shouldn't have a problem with that. Okay? Now, beyond that, there's other rules. Here's some rules for rounding off decimals. Let's take a look at some of these. When the next figure beyond the last digit to be retained is less than 5, use the shortened form unchanged. For example, blah, 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 blah is to be shortened to 2 decimal places. The third figure beyond the decimal point is 3, which is less than 5. The decimal is rounded off to the number 2. So this is just typical rounding systems, okay? Whenever you're rounding up to whatever decimal you want to keep it at. For example, if I have 4732 and I only want 2 decimal places, then I take it from that to 4.7. I look at the 3. Is it less than 5? Yes. So I just leave it as it is. There's no reason to put a 0 or anything else. If the value was 4752, then it would round off at 4.8 because I would be taking this up. 5 and up, you round up. 4 and or anything less than 5 rounds down. So 5 is the magic point to round up the next numerator or the next value or down. Okay, but that's simple rounding. You've done that no doubt in the past. And you can take a look at those whenever you run into situations. Typically, again, the CAD system will round off for you and take care of those features. You have just to set the precision. Now, the precision means basically how many decimal places do you want? Do you want 3? And here's the term, precision. Do you want 3 decimal places? Do you want 4 decimal places? Or do you only want 2 decimal places? You set that, and then it will automatically round up or round down for you based on the dimension. So that's the kind of thing that it handles on its own. Alright. Now, fractional dimensioning, we'll skip that because we typically won't use that in manufacturing. And the only time you really use it is if you're in architectural or perhaps structural drawings, which is also a form of architectural. Let's take a look right here, though. Metric dimensioning. Very similar to the decimal inch dimension. It's a point system, still based on tens of units. However, it's obviously different in its overall base. Here's a key number to remember, though, while we're talking about this. Box around that. Key thing to remember with decimal dimensioning is that 1 inch is equal to 25.4 millimeters. Now that value could be greater, but for the most part that'll get you a long way in terms of conversion. You can always remember that. Now if you want to know what centimeters is, just move the decimal place over. 1 inch is equal to 2.54 centimeters. If you remember this one key conversion, this one right here, it will take care of you for most of your calculations. Using that value allows you to switch back and forth in many different dimensions. So remember it, 1 inch equals 25.4 millimeters. Now, in terms of metric dimensioning and some metric dimensioning rules, you'll notice that the metric system is referred to as the SI system, or Système International d'Unités. I don't know what that is. International System of Units. And the SI abbreviation is what indicates, that's a little bit too close for that, sorry. The SI system is what identifies the metric system. Now, the basic rules. One kind of weird thing to us is that, number one, it points out that in America, with the SI system, okay, we separate our decimal points with a period. However, in some countries, they'd use a comma. And let me assure you, it's very weird in terms of design. I've had a couple situations where I've had to switch over, working on some houseboat designs, and we had to do a couple European boats, and they used the comma. Very confusing, but just understand that if you see it, it's not actually separating tens and thousands or hundreds of thousands from millions. It's actually their version of a decimal point. So keep that in mind. Couple basic rules. Basically, if a number is less than 1 millimeter, a 0 should precede it. Digits in the metric dimensions are not to be separated into groups by use of commas or spaces. So you basically don't use commas for values like 100, or I mean a million, sorry. You don't use spacers for that. We won't use a spacer for 1,000. We do that in the English system, but in terms of SI, for SI, you just go 1 0 0 0 1 or 0 0 0 and then 1 0 0. Okay? Remember that too. And use metrics that are multiples and submultiples of thousands, such as kilometers, kilometers, and stuff like that. And you can kind of get that figured out without too much of a problem. And then it says, do not mix SI metric units with units from a different system. The only time we mix them, and we don't really technically mix them, is when we do dual dimensions, or dual dims. And that's when you have one number and then a space, or I'm sorry, not space, a parentheses or brackets with the second number, or the English equivalent. So if I were going to dual dimension 1 inch, I would do something like this. Here's the dimension. There's my 1 inch, or maybe 1.0, and then I would have 25.4 would be the actual way the dimension shows up, or however your particular CAD package works. Now, on that same note, we have some information regarding dual dimensioning and the different formats. Again, this is fairly pretty much controlled by your CAD package and your choice. You've got a couple of different ways to lay it out. One can be one over top of the other, one can be in brackets, and you can switch back and forth. So, not a big deal there. Deal with whatever package you're dealing with and you'll be fine. Now we move on to the whole concept of how to dimension particular objects, aka dimensioning features for size. Now this section is where you really want to spend your time in marking in your book, because all this information that you're going to see is easily repeated down the line. All you have to do is flip the page you're interested in and go for it. Okay? So, starts off with cylinders, and I want to draw your attention to the bottom of page. By the way, the top of the page there has the dual dimensioning stuff, but the bottom of page 289 has a great little detail for us on how to dimension a cylinder, meaning how do I dimension an object like this in its different formats, from looking above, from looking at it. Whoops, didn't mean to do that. How do I dimension it? And here's all you need to know. When you're looking at it from the top, throw your hidden lines in, or and center lines as needed. When you're looking at it from the side, dimension it like so. You have a size dimension and a size dimension, and when you can't tell it's a circle, throw the diameter symbol in front of the actual value. Easy enough. Here's another case in point. When dealing with the stacked cylinders, again, dimension, when you can't see the circle face, throw the diameter symbol in front of it. And when looking at it from above, simply throw the diameter symbol there. And here's another format, however, is not as easy to see as this one. So, that's how you handle cylinders. No problems there, right? So mark this page in your book and somewhere that says dimension cylinders. That way you can find it easy and look it up. Up the top of the page in 290 we have how do you dimension arcs, circular arcs. Well, it's all with radiuses, either from the inside of the arc or from the outside of the arc. Several different formats. Doesn't matter, just pick one and go with it. This is the typical for the small fillets, and typically for the larger arcs, you put your check mark, not check mark, sorry, you put your center mark in, dimension to the center mark, and then show the actual radius value. Notice they all have R in front of them. That is key though in arcs. Radiuses are controlled by arcs. And this page shows you a lot of good practices for particular radiuses and corner radii. It even shows you what not to do. For example, it shows you to dimension to a true value, or at least list true, and then not to just show it this way when dealing with oblique angles or anything that is sort of concealed. And even shows you a shortened radius technique down here at the bottom of the page. So a great little page for radius features and arcs. Now, on the next page has a key piece of information that you want to take a look at, and that's what to do with hidden features. Alright, now, this is on the bottom of page 291, and it's important you pay real close attention. How to dimension a hidden feature. Well, first of all, we hardly ever dimension to a hidden feature. You always draw to these object lines whenever possible. If you can't show something or can't dimension it without using hidden lines, then switch to a section view and dimension it. Okay, still not trying to dimension to a hidden line. However, if you're going to have to dimension something that's a hidden line, you can do it in this format. A partial sketch section that actually locates a dimension based off a hidden line. So, rule number 1 with hidden lines, don't dimension to them. For example, none of this, here's the hidden, nothing dimensioned. Down below, there's the hidden stuff, not dimensioned. See, they dimension when they have section views. So, your first priority is don't dimension to a hidden line. If you get wanting to, draw a section and dimension the section. If you have to, then you can use a partial section view and use it in this format. Okay? But for the most part, don't dimension to a hidden line is the rule here. Okay, we're going to stop the video next, and so you can start another one. We'll pick back up on the same page, and we'll see you shortly.